My talk is called "And Polynomials Begat Polyterms," and my nickname is the Heretic because probably what I'm doing is heresy. I thought, since I love math and chemistry, I thought math is the chemistry of numbers. So, you know. Two dedications. One is for my University of Baghdad School of Engineering classmate, Dr. Saad Jassim, PhD in chemical engineering, water treatment consultant, and ozone treatment consultant, expert. A classmate, I'm very proud of him. I saw him a few weeks ago in Vegas, ozone conference, and this man has spent 34 years, he lives in Canada, in Windsor, doing all kinds of stuff and helping better water treatment and getting rid of pollutants like pharmaceuticals that are making their way into the drinking water. Second dedication to my chemical reaction design teacher at the University of Michigan in 1979, Dr. Fogler. He passed away. We both loved reaction kinetics and numerical analysis. I got his attention one day when he was solving a problem, and he said something 1 over ln of 100, and what's that? And I said 4.60517. And he kind of looked at me for 2 seconds, and he treated me differently from the rest of the students from that point on. A question from the past. This subject has come out. In previous HHC conference, we asked, what would be the impact on numerical analysis, curve fitting, number theories, and so on if legacy mathematicians like Newton, Euler, and Gauss had programmable calculators? And let me add fuel to the fire and said, how about today's laptops? Now, this talk focuses on polynomial curve fitting, what the impact might be. Legacy mathematicians push things to the limit of their computing resources. Some did it by hand, all by themselves. Some who were teachers would solve a problem and then give it to their students to see if anybody comes out with a matching answer. And some hired other people who could do calculations by hand and of course recheck it. Very painful.
Isn't
yes.
More math becoming very computer intensive?
Yeah.
In general.
Yes. Now, despite that handicap, they came out with methods like Gaussian quadrature, linear multiple regression. I mean, they really pushed things to the limit. Now, even non-programmable analog slide rules did not make things a breeze because they made division and multiplication a little bit simpler, albeit at the cost of accuracy. But other than that, I mean, they had maybe tables, sine, cosine, whatever, but they didn't really, I mean, try to do linear regression with a slide rule, good luck. And then it happened. Now, the HP74 was the first calculator that killed the slide rule. It was the first step forward. The second step forward came 50 years ago when the HP65 came out as the first handheld and personal programmable calculator. With them, they had math and stat packs that came out, and they solved many complex algorithms, legacy algorithms. For example, like if you wanted to do linear regression, well, here's a magnetic card for the 65. You want to do numerical integration, here's a magnetic card. Suddenly it became a breeze. The computations are reliable. All you have to do is enter the program, enter the data, and you have your answer. This was a historical breakthrough, the dawn of personal computing. You can take it home. And our community, PPC and Chew clubs and chapters saw the light. This was really a monumental event. And we are still here today because of programmable calculators. Now, the topic looks at classical polynomials versus the new polyterms. So in classical polynomials, when we look at the polynomial, we have the equation here. Let me see. Oh, whoa, okay. I hear you, Richard. Okay. Well, and this is, I call it term zero, the intercept, and then this is summation of n terms, and we raise x to an integer I. Now, typical power p of I is I. So the first term has power of 1, second term power of 2, and so on. Sometimes we approximate sine cosine with either even or odd integer. Even powers, p of I is 2 of I. Odd power integers is 2 times I minus 1. So general term of the power p of I is a times I plus b, where a is 1 or 2, and b is 0 or minus 1, and I is the term number. We don't think of it that way. We just plug in those powers, but I'm trying to make you look at the conceptual part of it. Okay. Regression with classical polynomials, we form a Vandermonde matrix X. I'll show you one next slide. For the polynomial of order m. Typically, the first column, or any column should, but typically the first column has ones. That's to calculate the intercept. Then the second column has the values of x values for each observation. Third column has the squares of the observed values, and so on. So for a polynomial order of m, we have m plus 1 columns. This is a Vandermonde. These are the observations, and this is the Vandermonde matrix. And we want to solve for beta 0, beta 1, and so on. And then the epsilons are the errors, randomly distributed errors. To solve the polynomial coefficients in matrix form, we have the Vandermonde matrix X. We take the transform of it, multiplied by itself. Now, the Vandermonde matrix usually is a long matrix if you have a lot of data. It typically has more rows than columns. But when you transform it and multiply it by itself, you get a square matrix, much smaller than the original one. Same number of columns and same number of rows. And if you invert that product and multiply it by transform of x of t times the observation, you get your coefficients b. So, the product of xt times y is the summation of y times x to various powers. So, okay. Meanwhile, back at the ranch, let's go back to the equation of the polynomial power. P of I equals A times I plus B. So far, we had simple cases where B was 0 and A was 1. What if A and B are not integers? We change the tempo of the polynomial power sequence and create polyterms in hope of getting better curve fitting. That's the challenge. If you remember in 2008 in Corvallis, I presented a first type of polyterms, which I called the Shammas polynomials, because I used my last name because I did not want to clash with some professor of math who said, no, I'm using this term, and, buzz off. So, and if you remember, well, the form here, instead of just x to the I have x to the power a times I plus b. Or more generally, x to the a times p of I plus b. Why? Because p of I could be simply linear, that's easy. Could be reciprocal, even a natural log of 1 plus I. Now, my current preference is p of I equals I. That's because it's simple. The other stuff is very esoteric. Now, a good choice is I is less than 1, and we select a small value for b. Now, the above choice shrinks the powers of the polynomial, and small powers reduce the round-off errors when performing polynomial or polyterm regression. Now, in each term of the Shammas polynomials, we use the same values for a and b. So we really only have two unknowns in the powers for the whole polynomial. And determining the best value of a and b requires an optimization of the best polynomial. So we have now the concept of polyterms. We have two layers. We have one layer is the least square regression part, and on top of it, an optimization. And optimize the function, which is really the least square calculations, to get the best, the unknown powers. Now, the simplest polyterms appear when we say, hey, let's assign 0 to the shift b and keep a less than 1 and use p of I equals 1. So we have something like this, very simple. That becomes simpler. Now, if we assume a equals half, meaning powers progress in half, in square multiples of square root, we can do even a third or even a fourth. But the half generates good results. Now, in this case, since we're choosing a and b, they're no longer unknown. We're imposing them, and we don't need to do the optimization. We simply transform the x, for example, into square root of its values, and we can go to our preference of software that does polynomial regression, like in Excel or Python or MATLAB, and proceed as usual with x being x squared, you know, the transformed x. And we can do that. There's no optimization needed in this case. Another version of the simplest polyterms includes terms with both positive and negative integer powers. And this extended polynomial has to exclude values x equals 0. Now, the symmetric extended polynomials now there's two flavors. The symmetric extended polynomials has the same number of terms with positive and negative integer powers, and it's defined by this. So it's I to 1 n, so this is the same n. You have the intercept, and then these are the positive powers and reciprocals. You can't use x equals 0. The asymmetric extended polynomials has a different number of terms with the positive and negative integers. So you define them by x, n, and m. M is for the reciprocal terms, and n is for the regular powers. But all these are integers. Optimizing the symmetrical extended polynomials can use a single loop because you're doing integers, so that's easy. You don't have to do optimization algorithms. And so you try each one, and then you say which one gives you the highest adjusted R-square value. Now, in the case of asymmetrical, you have two factors, the number of negative powers and positive powers. So you have a nested loop, and again, because these are integer values, it's easy. And you do the same thing. You try the different powers for the extended polynomial, and select the one that gives you the highest adjusted R-square value. Another more recent polyterm is called the quantum Shammas polyterm. Now, first of all, it's not related to quantum computing, so I want to make that clear. It's inspired by the concept of probabilistic orbits of electrons in atoms. At one time, the physicists and chemists thought the electrons have fixed orbits, and you know that. But then quantum physics came and said, "Cool your jets, Mary. Not so fast. It's a probability." And that gave me a thought, like, oh, okay. Instead of having a fixed value of a, why don't I make a of I a probabilistic value around I itself? So a of I is a random value in the range, say, 0.7 plus I minus 1 and less than 1.3 plus I minus 1. So the first one will be 0.7, 1.3. For the second term is 1.7, 2.3, and so on. And Each term will have its own A of I value. Now, this requires some more serious optimization. There's also the double power polyterm. This is a little bit weird because we have the equation here, and I've transformed z is x to the power log 10, some power of x, and taking account the term number. And it turns out that if this is a linear term, you get the best, surprisingly the best results. I've tried linear, quadratic, and cubic, but the linear was the best.
You're
Yes.
missing a lot. No, you're not. I see it now.
Yeah. And again, when P of Ix is a linear equation, we get very good results. I had tried many different models, and that's among actually surprisingly the best. And we can also do a shifted Shammas polynomials where we can have x becomes z minus a shift value, and x in this case, I'm mapping it into x minus minimum x over maximum x minus minimum x plus 1. So that gives me z in the range of 1 to 2. And then I can select s of I as a random number between -1 and 1 for all the values. And we can also create a shifted quantum Shammas polynomial. So we can introduce the concept of shifting in all of the other ones too. Okay. Now the general templates of polyterms, we have polyterms that resemble polynomials, except they have non-integer powers. We can have polyterms that resemble extended polynomials with positive and negative powers. We can even have polyterms that resemble rational Padé polynomials. These are where you have ratios of two polynomials, but they have non-integer powers. Now, optimization, legacy constraint optimization methods may not work well because the stuff has a lot of local minima and all that, and these algorithms will easily be led astray into giving you not so good answers. I use evolutionary optimization algorithms. Most use trust range values, because when I said the values of the coefficient are in a certain range, and a narrow one too. It works well because the unknown coefficients here, and I can also use random search optimization. It's very simple to code and works fast, and it works well because these ranges of the coefficients are relatively narrow. If they were very wide, then it would not be very efficient. So function to optimize, minimize, calculates 1 minus adjusted R-square value. So you want it to be as close to 0 as you want, meaning the adjusted R-square value itself close to 1. Computation efforts depend on the number of observations you have, the number of terms, and the transformations you're doing. So if I given a function f to minimize, it takes data, parameters to optimize, and I build a regression matrix, and then I solve it for 1 minus adjusted R-square value. So I can do the random search optimization, and I have lower and upper range for each variable. So that makes it easy. And I set a maximum number of iterations. And I can be generous there. It could be 10,000, 100,000, because the process is very fast, typically. It can be very high because it's slower when you use evolutionary algorithms, although those are more better. But in our case, we're not losing much by using simple random search. Here's an example like set to optimization. Set best fx at a high number first, and then I iterate from 1 to max iter. I generate a random vector for variable x to optimize within the given lower and upper ranges for each variable. I calculate f of x, that's the least square value, that's 1 minus adjusted r square value. And I say if this value is less than the best fx, then I update best fx and the best x to the current value. And once I do the iterations, I return the best fx and the best x. Very simple. The good news is several months last year, I put some of these programs on the HP Museum website. So the website has actually the examples, and this talk gives a little bit more explanation of the concept in more details. So I have Shammas polynomial curve fitting, quantum Shammas polynomial curve fitting, symmetric Shammas polynomial. This is symmetric, but the powers are not non-integers. And then symmetric quantum Shammas polynomial. And then above programs use random search optimization. Very easy to code in HP calculators. And those were, sorry, that's one. Yeah, those were for the HP prime. You'd find them in the HP prime area of the calculators. And for the HP71B also, I had the Shammas polynomial curve fitting, the quantum Shammas polynomial curve fitting, and they use the math ROM. Why? Because I need the matrix operation to make least square fitting much easier or much shorter. And they all use random search optimization very fast. You can give it 10,000, 100,000, and you don't have to wait a whole lot of time to get the answers. Because the polyterms use random processes, whenever you run the same data, you will get slightly different results. Unlike straight polynomial regression with integer powers, that's deterministic. The same machine running the same software will always give you the same results for the same input data. Here it's different. So you can have successive runs and you'll have results with some variations, and you can either use the same model and then average out. When you're doing predictions, you can take, maybe you make 5 runs and then you average the results of each one. Or you can use different polyterms, and again, average out. That's an inspiration from machine learning ensemble approach. Closing comment, polyterms tend to offer better curve fits than classical polynomials when the latter does not model fitted data function well. Like if we have e to the x sine cosine, polynomials will win hands on, no problem. But if it's a little bit more complicated, like a Bessel function, or it's multiplication of Bessel function times the natural log and all that, then the polyterms can compete well. And if there's error in the data also, that gives chance for the polyterms to do better than regular polynomial. So now, better curve fitting does not automatically mean spectacular curve fitting. I've tested, and the data is in the jump drive. Some stuff is tough. And even the polyterms did better than the regular polynomials, but it's still like you scratch your head, you go like, that's a tough function to fit. Yes.
Now, when you say better, let's say I have a plot of data.
Yeah.
And I want to curve fit the data.
Yeah.
Now, I may do that with different methods. Now, would the better method
Better means like your adjusted R-square value is higher, but it may still be 0.7 or 0.8, not 0.999,
Well, what I'm saying is that if I have the data points and I have this curve, one method, and this curve, the other method, if the area under the curves is less for one method than the other, is that the method?
No, that's the least square. No, the least square error, the curves passing in between the points. You calculate the sum of square error in each point, and there's the regular polynomial versus the polyterms, and hopefully what I'm saying is sometimes the polynomials will bomb out, but the polyterms will do great. But sometimes the function is really tough to model, and the polyterms will do better, meaning a higher adjusted R-square value, but it's still not 0.99. I mean, like polynomials may give you 0.5, and the other one may give you 0.7. You know, it's better, but it's not a guarantee that's spectacular. That's and so, I've also tried, and you will find the stuff in the proceeding. I've tried for 2 independent variables and 3 independent variables, but the question is, when you raise the order, then the cross products start to increase. So with 2 independent variables, maybe I go to the cube, and then with 3 independent variables, just squares, because you have so many cross products. So going back to answering the question, computing tools like programmable calculators and personal computers allow us to implement algorithms that legacy mathematicians could only dream of calculating with ease, if at all, because they may have thought about this stuff, but they go, boy, this is so complicated, it'll take years and years and years to just calculate one run. These tools enhance our math stat skills to legacy genius levels compared to so. And you don't have to worry about this because Eric downloaded this stuff. There's one file introducing the new world of polyterms that it's in the main root. You don't even have to look at the whole thing, but it has like what the models are, different types of models, and then the summary, and including sorting them out in best to worst models. And that's how they do polyterm curve fitting enrichment. Thank you.